Sketch the graph of the function. In this example, we have a two-piece function. The top piece is defined as x plus 5, but only when x values are less than or equal to -4. And the other piece to the function is the line 1/2 x minus 3, but that's only defined when x is greater than -4. Now, from our previous experience in graphing lines, we know that this top piece is a line with a slope of 1 and a y-intercept at 5. Over here in the bottom right of your screen to your graph, that would be a line with a slope of 1 and a y-intercept of 5. However, we can't draw the entire line. We can only draw the parts where x is less than or equal to -4. In the pink, I have subbed in -4 and a number less than -4, and just to make it easy was -5. This is just to give you a rough idea of where your graph will exist. When x is -4, our answer was 1. You pair those up, -4, 1. That's the ending point of the top piece. When x is -5, our answer was 0. So that tells us -5, 0. Excuse me. Now, since we know that this is a line with slope 1, we know that the line will go up 1, right 1 from point to point. We have to stop it here at -4. The second piece is a line with slope 1/2 and a y-intercept of -3. And in blue, a y-intercept of -3, a slope of 1/2 is up 1 over 2, up 1 over 2, and you continue that trend, and that gives you the proper slant to draw that line. Even though the bottom piece is not defined for -4, you can still substitute that in. If you plug -4 into your function, 1/2 times -4 minus 3 gave us -5. So the point -4, -5, we can put an open circle on that point. That way we technically don't count it because the x value of -4 is already used up. And then from here we can do up 1 over 2 repeatedly if you need to, and we can sketch our line. Be sure the x values you pick fit the particular piece that you're trying to draw. -4 doesn't fit the piece, but it doesn't mean you can't plug it in. It just gives you a location indicator. 0 is greater than -4, so when you plug a 0 in, half of 0 minus 3 is -3. That point counts because it fits your criteria. In our second example, we have another piecewise function defined as 3 plus x when x is less than or equal to 1. And then the other piece is defined as x squared minus 3 for all values of x greater than 1. The top piece is linear. It has a slope of 1. It's a line with a slope of 1 and a y-intercept at 3. So in blue, I know that line would look like this. Now again, we can't draw it in its entirety, only for values of x 1 or smaller. But because we know it's very predictable, a y-intercept of 3 is slope of 1, we know that 0, 3 is a point on the line. If we go up 1 over 1, that takes us to the point 1, 4. Since 1 is the maximum number that piece can take, 1, 4 is the last point we can plot on it. Any value of x less than 1, we can go ahead and draw the line for that part. Once we get to values of x greater than 1, we have to switch over to this quadratic function, and we're going to draw a parabola, more specifically a partial parabola. Again, even though the function is not defined for 1 exactly, that doesn't mean you can't plug it in to get an idea of where the graph would be. G of 1 at the second piece, again, we can't count the 1, but it doesn't mean we can't plug it in to get an idea of where it's going to start. 1 squared minus 3 is -2. So at the point 1, -2, we're going to have to use an open circle And that says that we know we can't count that point, but it gives us an idea of where the second piece starts. Pick another number, make sure it's greater than 1. 2 is convenient. 2 squared minus 3, that's 1. So that tells us the point 2, 1 is definitely on the graph. And because we've graphed parabolas, we know that the graph will curve upward. This is the graph of your piecewise function. The top piece is a line, but once you get to 1, you switch over to the parabola. Now we're going to switch over and discuss domain and behavior of graphs near the values that are excluded. First function is 3 over x minus 2. One of the no-nos in math is you don't want to divide by 0. What value of x creates a 0 denominator? It's 2. Now, since we don't want the denominator to be 0, we just can't use an x value of 2. The domain is all the good x values, so really it's easier to find the bad ones and toss those away. Our domain is all real numbers such that x isn't 2. Any other number is fine. Now, many times on a rational function, when you have a number specifically tied to x that gives you a 0 denominator, you're going to get a column of dead space where a graph isn't going to exist because the function is undefined. The behavior around this excluded x value, you can test numbers like 3 or 4. If you really want to get close, and what we're going to do on the next example is we're going to pick real close. So to be honest, numbers like 2.01 or 1.99, those will give you a good indication of what happens around an excluded x value. All right, so back to the ink part. Left of 2, numbers smaller than 2, you could use like 0, -1, +1. When you substitute those in, f of 0 is -3/2. That gives you your y-intercept. F of -1, you get -1, so the point -1, -1 is on the graph. +1, that's still less than 2. That gives you -3, so the point 1, -3 is on the graph. You start getting a trend of the closer you get to 2 from the left side, and this superscript of a negative is, the way you read this is, as x approaches 2 from the left, as you get closer to 2 from the left, your function values will get increasingly more negative. So this function, as x approaches 2 from the left, your function values will approach negative infinity. You get on the other side of 2, numbers like 2.01, 2.5, 3, or 4. Those are all values of x you can sub into your function to get an idea of what happens to the graph when you approach x from the right. A superscript of plus is approaching from the right. So f of 3 was 3, f of 4 is 3/2. If you pick a number like 2.01 and substitute that in, you'll get a value like 300, really large. The closer you get to 2 from the right side, the larger your function values get. So the way you would write that is, as x approaches 2 from the right, your function values approach positive infinity, and that's this blue inked. Both pieces make up your graph. It's just the behavior near that excluded x value is what you got to watch out for. And it is worth investigating. In calculus, you see that a lot. Our next function, 2x over x squared minus 9. This denominator is 0 when x is either -3 or +3. That's the difference of 2 squares, so it makes it easy to factor. Now remember, domain's all the good guys, so our domain is all real numbers such that x isn't -3 or +3. I've got those marked on the grid over here. Testing numbers approaching -3 from the left, you take numbers like 3.01. That's smaller than -3, but just barely. If you substitute -3.01 into your function, just carefully place it in for the x's, you get approximately a -100. So that tells us as x approaches -3 from the left side, our function values get more and more negative. Now, on the other side of -3, when we approach -3 from the right, and that's what this notation means, x approaches -3 from the right, we pick a number like -2.99. That's real close to -3, but it's on the right side of it on a number line. Substituting this into your function, you get about approximately a +100. These are just ideas of whether your function values get large or small. So the function approaches positive infinity the closer you get to -3 from the right side. Our other excluded x value was +3. Approaching 3 from the left, we pick numbers like 2.99. So in the hot pink over here, I've plugged 2.99 into our function. We get about a -100. That tells us that as we approach 3 from the left side, our function gets increasingly negative. And then finally, as we approach 3 from the right side, we could pick numbers like 3.01. It needs to be greater than 3, but pretty close to 3. This will be done in the green ink. I picked 3.01. If you sub that into your original function, you get around 100. So the closer you get to 3 from the right, the larger your function values get. And that's the way you interpret this behavior around an excluded value. As x approaches 3 from the right, your function gets increasingly large, more and more positive.